Introduction. Many business and economic activities are concerned with the problem of planning. If the supply of the resources are unlimited, the need for linear programming problem would not arise at all. In each case, limited resources are available, and to make use of these resources, programming and planning problems could be formulated to maximize or minimize a linear form of profit-cost function whose variables are restricted to values satisfying a system of linear constraints. The term programming refers to the process of determining a plan of action. Linear programming is a technique for determining an optimum schedule of independent activities in view of the available resources. Linear relationship between two or more variables is the one in which the variables are directly or precisely proportional. The general LPP calls for optimizing, between brackets we mean maximizing or minimizing, a linear function of variables called the objective function, subject to a set of linear equations and or inequalities called the constraint or restrictions. The linear programming can be used for optimization problem if the following conditions are satisfied. 1. There must be a well-defined objective function which is to be either maximized in the case of profit production or minimized in the case of cost, men, materials, etc., and has to be expressed as a linear function of decision variable. Here we mean by decision variables whatever products like profit, like materials, or the unit of cost, or the unit of profit. Number 2, there must be constraints on objectives function, and these constraints are expressed as a linear equalities or inequalities. 3. There must be an alternative course of action. For example, a given product can be processed by 2 different machines, and the problem may be as to how much of the product is to be allocated in each machine. 4. Another necessary requirement is that decision variables should be interrelated and non-negative. The non-negativity condition shows that linear programming deals with the real life situations for which negative quantities are generally illogical. 5. The resources must be limited. In most linear programming problems, the decision variables are permitted to take any non-negative values that satisfy the constraints. There are some problems in which the variables have integral values. These problems are not LPP, but very often they can be solved by LPP techniques, and the values are then approximated to nearest integers to satisfy the constraints. Linear programming is a mathematical modeling technique in which a linear function is maximized or minimized when subjected to various constraints. This technique has been useful for guiding quantitative decisions in business planning, in industrial engineering. Linear programming comes under the allocation problem. Is a problem which involves the allocation of given number of resources to certain job. Let's continue the previous slide, which highlights the essence of LPP. The objective of these problems is to optimize the total effectiveness. For example, to minimize the total cost or to maximize the total return. Linear programming is the combination of the two terms, linear and programming. The term linear means that all the relations in the particular problem are linear, and the term programming refers to the process determining particular program or plan of action. Let's see mathematical formulation of linear programming problem. The procedure of mathematical formulation of LPP consists of the following steps. Step 1. Identify the decision variables of the problem. Step 2. Formulate the objective function to be optimized, maximized, or minimized as a linear function of decision variables. Step 3. To formulate the constraints of the problem, such as resources, as linear equations or inequalities. Step 4. Add the non-negativity condition. The non-negativity condition. This is known as a procedure of mathematical formulation of linear programming problem. This is the process of mathematical formulation of linear programming problem. Let's see. We mentioned previously that the components of linear programming are 3. First is objective function. The second component is a constraints or restrictions. The last is non-negativity condition. So the components of linear programming are 3. 1. Objective function. 2. Constraints. 3. Non-negativity condition. Objective function explains the target of the function, either to maximize profit or to minimize cost, or it indicates the other target of the function is to minimize cost. Let's see what stands behind these practically, what stands behind these 3 components. Generally, linear programming problem can be stated as follows. Find x1, x2, x3 up to xn which optimize the linear function z equals c1 x1 plus c2 x2 up to cn xn. So Z stands for objective function. In case of maximization, C1, C2 and Cn is said to be the profit of 1 unit of product. In case of x1, C1 indicates the profit of 1 unit of x1, where C2 refers to the profit of 1 unit of x2, and Cn respectively denotes the profit of 1 unit of xn. In case of minimization, C1, C2 and Cn express the cost of one unit of product x1, x2, xn. In particular, in case of minimization, C1 stands for the cost of one unit of x1, where C2 stands for the cost of one unit of x2, up to Cn stands for the cost of one unit of xn. This is what about the objective function. Let's move to the constraints or the restrictions. Put into account that fact. The components of LPP are three: objective functions, number two, constraints or restrictions, number three is non-negativity condition. So let's move to ST, or subject to the constraints. Okay, we assume that the manufacturing or the fabric or the process of production passes I stages or three stages. Let's see. Now, just look to the constraints number 1. Put into account this constraint doesn't explain that the problem is about maximization or minimization. Okay, now A11 x1 plus A12 x2 plus A1 j xj up to A1n xn. Once we are talking about the constraints, that means we are talking about the cost of production. You have to consider that the company has limited resources to produce a certain quantity of products. Now, A11 is the cost of producing one unit of x1. A12 is the cost of producing one unit of x2 up to A1. N is the cost of producing one unit of xn. In case of maximization, the constraint must be less or equal. In case of minimization, the constraints must be more or equal. So more or equal B1. P1 stands for resources, whatever resources, time, energy, men, raw materials, whatever. So we have to produce total products of x1, x2, xj and xn. They must don't cost me more less than P1. Should be less than P1. The total cost of this product should be less than P1, because at this stage the company has very certain, very restricted resources equal B1. In the contrary of case of minimization, should be more or equal B1 logically. Now move to the constraint number 2, where A21 x1 plus A22 x2 up to A2n xn also less or equal or more or equal B1. Let me emphasize that B1, B2, Bi, Bn stands for what? Stands for available resources for this company of fame. Now A21 is the cost of 1 unit of x1, whereas A22 is the cost of 1 unit of x2 up to A2n is the cost of 1 unit of xn at the first stage or in the second machine. The constraint number 1 illustrates, for example, the first machine, and constraint number 2 illustrates the second machine or the second stage, whatever. Now the cost of 1 unit of producing 1 unit of x1 plus x2 plus xj plus xn should be less or equal P1. It must not cost me more than P1 because I have limited resources. On the contrary, in the case of costs of or minimization, should be more or equal to compensate the total cost. Again, we can move to the third machine or third stage, where AI1 x1 plus AI2 x2 plus up to AIN xn. This is explains the stage number 3, or explain the process of production in the third machine. This is about the constraints. The last component, which is a very significant component, is non-negativity condition. Generally the company either to produce x1, that means x1 more than 0, or not to produce, that means x1 equal 0. So non-negativity constraint means the quantity of products either equal 0, no production, or there is a production, that means more than 0. The non-negativity condition is a very important and very significant component in linear programming. So this is generally about the components of a linear programming. It's generally about the components of linear programming. Linear programming is a very vital, very precise mathematical technique. We have to put serious consideration to this approach. Is very significant, very helpful in the process of understanding the object, the operation research, or engineering management. Okay, let us summarize the previous linear programming problem theoretically and start with 4 steps. Step 1, to write down the decision variables of the problem. To write down the decision variables of the problem. What do we mean by decisions variables? The list of products x1, x2 up to xn, shoes, t-shirts, whatever, watch, TV, cars, whatever, car 1, car 2, Mercedes, whatever, Land Rover, and so on. So firstly, we have to write down the decisions variables of the problem, usually illustrated by x1, x2, x3 up to xn. Number 2, step 2, based on step 1, we need to formulate the objective functions to be optimized. To be optimized means maximized or minimized as a linear function of decision variables. We mean by a linear function of decision variables objective function. That means objective function expresses a linear function of the decision variables. Step 3. Step 3 is about the constraints. To formulate the other condition of the problem, such as resources, markets, other constraints, interrelationship between variables as linear equation or inequalities in terms of decisions variables. So step 3 talks about the constraints under which the company should satisfy or should implement its function, either to maximize profit or to minimize costs. Step 4, it is about adding non-negativity condition from the consideration so that the negative values of decision variable do not have any valid physical interpretation. Now let us practically exercise the LP linear programming. Actually, how to formulate linear programming problem. Let us see the first example. A resourceful home decorator manufactures two types of lamps, says A and B. Both lamps go through two technicians. First, a cutter, and the second technician, a finisher. Lamp A requires 2 hours of the cutter's time and 1 hour of the finisher's time. The cutter has 104 hours, while finisher has 76 hours of available time each month. Profit per lamp A is $600 and per B lamp is $1,100. Assuming that he can sell all that he produces, how many of each type of lamp should be manufactured to obtain the best return? That means we are talking about maximization. So we have to design an objective function as the function of profit maximization. So the constraint should be less or equal as mentioned before. For the problem of maximization all time, the constraint should be less or equal. So to solve this problem, or to find the solution of this problem, so we need to formulate a mathematical model of the problem. So later in the next slide we can explain how to construct a table which help us in formulating the mathematical model of linear programming problem. Now let me emphasize the fact that the LPP should or must consist of 3 components: objective function, constraints, and non-negativity condition. So it gives, based on the logical of the problems, it gives that we have to design an objective function as profit maximization. So okay, based on the previous example, the problem states that there are 2 products, A and B. That means there are 2 decision variables. Instead of A, we can replace x1, and instead of B, we can replace x2. Now, as mentioned, also are 2 phases of production: cutting and finishing, and respectively There are two levels of profit. Profit of A or X1 and profit of B or X2. A requires 2 hours for cutting and B requires 1 hour for cutting. The total available time for cutting is 104 hours. Then product A requires 1 hour for finishing and product B requires 2 hours for finishing. The total available time of finisher is 76 hours. Now let the decorator manufacture X1 and X2 lamps of type A and B respectively. As we mentioned before, the objective function should be designed according to the level of profits. It should be max Z equals 600 X1 plus 1100 or 1100. Now check here please. There are two phases. That means we need to construct two constraints, one for cutter and the other for finisher. Two X1, 2 is the cost of 1 unit of X1. This is of cutting plus X1 for finishing. That means the total cost of producing X1 or A must be less or equal 104 resources. The next phase is for finishing. X1 for A and X2 for should be 2X2 for B should be less than 76. Now our objective function max Z equals 600 plus 1100 X2, 600 X1 plus 1100 X2. The constraints are 2 X1 plus 1 X2 less or equal 104. The next constraint is 1 X1 plus 2 X2 less or equal 76 hours. once we have two decision variables. That means the non-negativity condition is x1 comma x2 more or equal 0, more or equal 0. Okay, let's see the last version of the linear programming problem. Max z equal 600 plus 1100 x2. This is an objective function. This is an objective function. Subject to main constraints: 2x1 plus x2 less or equal 140, x1 plus x2 less or equal 76. The non-negativity condition is x1 comma x2 more or equal 0. Example 2. Abdullah, a retired government officer, has recently received his retirement benefits. He is contemplating how much money should invest in various alternatives open to him so as to maximize return on investment. The investment alternatives are government securities, fixed deposits of public limited company, equity shares, time deposits in a bank, and house construction. He has made a subjective estimate of the risk involved on a 5-point scale. The data on the return on investment, the number of years for which the funds will be plugged to earn the return on this investment as follows. Logically, the problem talks about maximization. Let's see in the next slides how Abdullah should construct his table of linear programming problem. Based on example 2, the construction of the table as follows. As mentioned by example 2, there are 5 alternatives to invest his money. Government securities gives 6% of return, and within 15 years, and the rate of risk equal 1. Company deposits gives 13 within 3 years, and its risk equal 3. time deposit 10%, 5 years, and risk equal 2. Equity shares 26 respectively, 5 respectively. House construction, it is 25%, and for 10 years risk equal 1. The man was wondering as to what percentage of funds he should invest in each alternative so as to maximize the return of investment. He decided that the risk should not be more than 4 and funds should not be locked up for more than 15 years. He would necessarily invest at least 25% in house construction. The requirement is how to formulate the problem as an linear programming model. Now check the 3 variables: the return, number of years, and risk, follows by 3 or 5 alternatives: government securities, company deposits, time deposit, and equity shares, and last is a house construction. Now, according to this data and information, we are going to design a suitable linear programming problem. Check the next slide. Solution: formulation of an LP model. Now, let x1, x2, x3, x4, and x5 be percentage of the total funds that should be invested in all given fund schemes, respectively. Objective function should consist of 5 decision variables. So the parameter or the coefficient 6, 13, 10, 4, you can find it referring to the previous table. So objective function, it is about maximization profit or maximization return. 6x1 plus 3x2 plus 10x3 plus 20x4 plus 25 x5. Now this objective function should be satisfied conditionally to the following constraints. 5x1 the constraint number 2, 5x1 plus 3x2 plus 5x3 plus 6x4 plus 15x5 plus 10x5 less or equal 15. Now the next constraint, x1 plus 3x2 plus 2x3 plus 5x4 plus x5 less or equal 4, and x5 more or equal 0.25, x1 plus x2 plus x3 plus x4 plus x5 equal 1. This is the linear programming problem or linear programming model of how the man should invest his money. And xj, this is a conditional non-negativity condition. Xj should be more than 0 for all j,